Our today's topic is work done. In physics, meaning of work done is different as compared to everyday usage. We say that when we apply force on an object covers some displacement in the direction of force applied, then work is said to be done. According to the definition of work done, the product of force and displacement is called work, or the dot product of force and displacement is called work. So work done is equals to dot product of force and displacement, that gives a scalar quantity work done. So work done is a scalar quantity. For understanding dot product, go through the lectures of chapter vectors and equilibrium. Let's take an example. For example, a person is holding chair at his arm's length for a few minutes. According to him, he might has done some work, but according to physics, he has done no work because he is holding the chair to support the chair, but he does not move the chair. So, because there is no displacement when force is applied on the chair, so work done is zero, because for work done, displacement should be covered when force is applied. Here you can see that this person is applying force on this object, and force applied by this person is making an angle theta, and due to applied force this object covers some displacement from this point to another point, and that work done is equals to F dot D is equals to W. Work done by constant force. Work may be done by constant force as well as by a variable force. Here we start work done using constant force. When we apply some force on a body, it moves through some distance in the direction of force. Then the product of force and displacement D is called work. Work done is equals to force into displacement. Let's say it equation number 1. In the following figure, force applied at angle theta on the body is shown. In this figure, this person is moving this crate and applying this force on this crate. When this person applies force on this crate, then this crate moves through some distance, and we can divide this force into its two components. We can resolve this force into its two components, Fx and Fy. The body is displaced by displacement d. We have resolved F into its components, Fx and Fy. When this person is applying force on this crate, the angle of force is theta, and we have resolved this force into its two components, Fx and Fy. So force is divided into its two components, resolved into its two components, Fx and Fy. Fx is equals to F cos theta and Fy is equals to F sin theta, and we have already discussed this resolution of vector in previous chapter, vectors and equilibrium. Go through that lecture for better understanding. So Fx is equals to F cos theta and Fy is equals to F sin theta. The body is displaced by force Fx and is given by W is equals to Fx d, and Fx is equals to F cos theta d. Actually, when a person is applying force on the crate is covering some displacement, and the component of force Fx is in the direction of that displacement. So work is done by the component of force, that is Fx, or W is equals to Fd cos theta. The above equation can also be obtained by resolving D into its components, keeping F and theta constant as shown. Here we can resolve D into its components. So we get W is equals to F dx, and dx is equals to D cos theta, and we get W is equals to When a constant force F acts through a distance d, the event can be plotted on a simple graph as shown in the following figure. The force applied on an object and the displacement covered by that object is shown here by the help of this graph, and the area under the graph gives us work done. The area under a force displacement curve can be taken to represent the work done by the force. The work depends upon force. The greater the force, the greater will be work done provided d and theta are kept constant. Distance. The greater the distance, the greater will be work done provided f and theta are kept constant. Angle. If angle theta is equals to 0 degree, then work done is equals to f d cos 0 degree, and we get work done is equals to f into d. So maximum work is done in this case. If theta is equals to 90 degree, then work is equals to fd cos 90 degree. Cos 90 degree is equals to 0. So 0 multiplied by fd gives 0. So no work is done by force in this case. If theta is equals to 180 degree, then w is equals to fd cos 180 degree, and cos 180 degree is equals to minus 1, and we get work done is equals to minus fd. In this case, work done will be negative. The work done against friction is said to be negative. Work is said to be 1 joules if a force of 1 Newton displaces a body by 1 meter in the direction of force. Work done by variable force. In many cases, the force does not remain constant during the process of doing work. For example, as a rocket moves away from the Earth, work is done against the force of gravity, which varies as the inverse square of the distance from Earth's center. So force decreases and does not remain constant. Force exerted by a spring increases with the amount of stretch, pulling, so force does not remain constant. In these cases, force is not constant. So due to variable force, work is done here. Work done by variable force. We shall now consider the work done by a force which is not constant. Now force is varying. Let us consider, for the sake of simplicity, that the force varies in magnitude only. In the following figure, the path of a body in xy plane as moves from point A to point B is shown. In this figure, an object is covering distance from point A to point B and force is varying. We have divided the whole distance into a small number of displacements, so we can divide the distance from point A to point B into a small number of displacements such as delta d1, delta d2, delta d3 plus delta dn. So delta d1, delta d2, delta d3, so on till delta dn. So we have these small number of displacements. We just simply divided distance from point A to point B into small number of displacements respectively, and the corresponding forces are F1, F2, F3, F4, so on till Fn. Total work done in this case will be, total work done is equals to delta W1 plus delta W2 plus delta W3 plus so on till delta Wn. So this force F1 making angle theta 1 and covering object is covering displacement delta d1. So for this force F1 and displacement delta d1, work done is delta W1. For this force F2 making an angle theta 2 and displacement is delta d2, work done is delta W2, and so on till delta Wn. This force Fn making an angle theta n and displacement delta dn. So for this force Fn, we can write delta W work done as delta Wn. In this figure, you can see that from this point to this point, distance is divided into a small number of intervals, into a small number of displacements, and we can sum up all these displacements to get the total distance. And these displacements are shown by the rectangle. All these rectangles are sum up to give the total area under the curve, and that is equals to work done, because we know that area under the curve in force and displacement graph gives us work done. So we can put the values of force as, for F1 we write F1 cos theta 1 because Fx component of force F1 is active, and for force F2 we can write F2 cos theta 2. For F2 force, X component of force is written here. For Fn force, Fx component of force is written here, that is Fn cos theta n. We can sum up all the work done and we get total work done is equal to summation sigma I is equals to 1 to n Fi cos theta I delta di. For summing up all the work done, we use this symbol sigma. Thus, the work done by a variable force in moving a particle between 2 points is equal to the area under the force F cos theta versus d curve between the 2 points as shown in the following figure. So, in this figure, the curve between Fx and displacement gives total work done. In this diagram, the total work done by the variable force is the area under the graph, shaded area. In this case, total work done is equal to limit delta d is equal to 0, delta d tends to 0, sigma I is equal to 1 to n, Fi cos theta I delta di. Here, delta d tends to 0 means we have taken very small displacement in this curve, and very small displacements are added sum up to give the total work done.